Alright, hey everybody, this is a tutorial on for the reference geometry for a shooter for a 9-inch ball. So you see I've started in a blank part studio. The first thing I'm going to do is I'm going to go ahead and start a sketch on my front plane. And I'll go here. And so the first thing we have to do is we actually have to draw what we're trying to shoot into. And so in this hypothetical situation, we're going to go for a goal on a wall that is, say we're going to be 135 inches away from it. See, it's quite far away. Let's get zoom deck out. Okay, and so now what we want to do is we can set the goal is going to be inset into the wall, and so we're going to try to shoot into this wall, into the hole essentially. So we can set this to be 98.25 inches, and then this is 29.25 inches back. And after that, I can set a line like just so. Set this to be 30 inches. This is just for, don't necessarily have to do this, it's just nice to have some reference. And I can make this symmetric here so it's nice and even. So I have all this set up and I've got it distanced away properly. And so around the origin is where we're going to put our quote-unquote robot for the reference. So we can do that with a center point rectangle, and I can hit Q to make it construction, draw my robot out, make the bottom edge, this is the bottom, like this is essentially the plane along which the wheels ride, and I can make that coincident to the origin. And then I can make it 6 inches high, just like the drivetrain for the intake, and I can make it 30 inches, or for mine it's 30, but if y'all's is 29, do 29. Okay, so now we got this in, and so the first thing we're going to do is we're going to draw in the first roller. And so basically the main flywheel that's going to do all the heavy lifting when we're shooting. So we can zoom in and let's put a circle down. We're going to use a 4-inch wheel, so we can dimension this to be 4 inches. And let's just kind of put it somewhere for now, just to get it dimensioned down. So let's say 16 inches up, and then back, let's say 6 inches from the frame, or maybe not 6 inches. Yeah, I guess that would be 6 inches. So because 6 inches from the, you know what I'm saying, that's right. And then to account for compression of the ball, what we can do is we can make another circle in here that is a 1/2 inch smaller. So we can make this, actually I'm going to do a full inch smaller because it's 1/2 inch smaller in radius. So we're going to make this a 3-inch circle. So now after that, we can add another circle here. This is going to help us dictate how we want our auxiliary rollers on our hood appear to be. And so the way we can do that is we can set, so we know it's going to be a 9-inch ball we're working with, and so we can grab the center point here and the outside point here, and we can make this 9 inches. And so now this is the path, like the channel in which the ball can pass through. So now we're going to grab 2 other circles, make them construction, and these are going to be our other rollers over here. Oops. Make them equal to each other and make them both tangent to this outside circle. So you can see, here, let me give you an illustration. We can set this to be 9 inches and grab, oh, I forgot. You don't dimension it from the center point here for 9 inches. You want to dimension it from the inside quote-unquote compression circle to here. That has to be 9 inches. That's the way the math will work. And so now you can make these 2 tangent and now you can see as the ball is traveling along this path, being compressed by this main flywheel. It's getting pushed up, and then it'll make contact with these rollers, which will impart some backspin on it as it leaves. So now we can make these, we want to make these, let's say 2 inches. And so we can set, now what we want to do is we can set the path the ball is going to take to the goal. So we can make that by setting a line right there, and then we can grab a 3-point arc and grab the midpoint of that and bring it way out here until we get to the very back of this goal here. And let's just set this to an arbitrary 350 inches, just get that nice curve, right? So now what we can do is we also want to set, like you see this is still blue, so that means that it can still move, and it's because this line is not at a fixed angle. So let's just go ahead and give that a fixed angle. Let's just say, 50 degrees. So next, the next thing we want to do is that you see this roller is nice and like defined. It has its full definition, but this one isn't. And so the way this shooter is going to work is we're going to have one motor about here powering this flywheel, which then is going to send a belt up here, and it will power these two. And so the power has to be belted from one to the other. And so the way we're going to do that to calculate how far away they're going to need to be is we're going to open up a new tab, and we're going to go to recalc, which is reca.lc. They did kind of a funny URL. So now we can go to belt calculator, and let's say, the first thing we want to do is to make this easier on ourselves is make a line in between the two. You see how I've made that? And I can just click on it, and you can check here how it's roughly 2¼ inches. And so we can go in here, and we want to have, so the way this works is you plug in your pitch diameter of your belt. We usually use either 3mm or 5mm. For this sort of application, we probably want to go with 5mm because it can apply more load. So let's switch that to 5. And this target center here is like, it'll give you the smaller belt and the larger belt than this target center, the first center distance. So we know that center, this line is our target center, the center to center distance between the pulleys. That's roughly 2¼ inches. So we can put in 2¼ inches here. And then next we can change what pulleys we want. And so we want this to just be an equal transmission of power. So we don't want any reduction. So we can set these both to 24 inches. It's also helpful here, it tells you the pitch diameter of the pulley if you want to put that in your drawing. It's roughly 1.5 inches. So now we can see that you can either do a 45 tooth belt or a 50 tooth belt. The 45 tooth gives us a center distance of 2.06, and the 50 tooth belt gives us a center distance of 2.55. Let's go with the 50 tooth belt to be 2.5591 inches. So now we can just grab this and do 2.5591. And now that's defined. So now these two will be linked with a belt in our final assembly. So now we got this mostly defined. For now, let's go ahead and start our idler, or our indexing pulley is the better way to put it. So the ball has to get some way from the intake, which let's say is over here. It has to get over here somehow up into this. And so the way we can do that is we can make another roller just like this and make it a construction line. Make the diameter be 3 inches. Let's say this is going to be a 3-inch roller, and then we can have another compression circle inside here, compressing down to 2 inches because we want that compression in the ball to handle it up. And so we're going to make this inner compression circle tangent with this outer path circle. And so now we have that, and now we want to have another circle. Make another quote-unquote ball circle for reference. So let's just make another one. Again, dimension this to 9 inches and make it tangent to the inside compression circle. And so now we're going to make yet another circle. It's a little circle heavy, this one. So we're going to bring it out here and make it tangent with this outside circle. And so this is going to basically, this location of this circle is going to give us the location of our indexer. And so just for some clearance issues, let's make it a 1/2 inch off of the base of the frame, or the top of the frame per se. And so now we have this location of this roller is fixed. And so you can see as we drag up the ball, it makes contact with the roller, it gets compressed, gets pushed up here, up and around, makes contact with the main flywheel roller, and continues up. And we can see how it continues up this way and hits those two top rollers, gives it backspin, and leaves the shooter. So now we've got our our flywheel, and then our rollers and our indexers. So now we've got to think about how we're going to power the whole thing. So we can power all these basically with one motor on either side, just mirrored. And then we're going to have another motor right here. So we're going to put another motor down right here. I think the diameter for a Kraken, which is the motor we're going to use, is roughly 2.26. Actually, let me check that really fast. And I can't find it. Oh yeah, here it is, 2.362. Make that construction. And let's say we're going to put it about here so it's out of the way of this whole path. So we're going to make another line from here to here, and this is going to be, the length of this line is going to be the center to center distance of the pulleys for this belt to this indexer motor. So now we can just grab this and say it's roughly 12 or 13 inches. So we can go with that. And on this one, we're going to keep it. Well, we're going to keep it as 5mm pitch because again we want that greater amount of load transfer. So we're going to set this target center to, let's say, 13 inches. But in this one, we're going to have the pulleys be a different ratio. We're going to set one of the pulleys be to 24, and then we'll set this one to 60 tooth. So we can see here we have this 170 gives us 12.5 inches, and the 175 gives us 13. So let's go with the 170. So 12.5477 inches. So we can grab that dimension and get this one to 12.5477. And you can see it still can float around because it just isn't fully constrained. So let's just give it an arbitrary dimension to place it down in place. So let's say, yeah, it looks about right. So let's just grab it 3 even. So now that is we've got this motor position fixed where it'll have a 170 tooth belt all the way here with a pulley here and a pulley here, and it'll drive this one correctly. So this one is a little bit more complicated. So because first we have to have a motor. Let's draw that motor out. We can set, instead of having to dimension this one, we can just select them both and hit E. And because we've already dimensioned this one will grab the dimension from here. So for the power transmission here, we're going to have a pulley on this motor going with a belted over to this flywheel, which is this one's going to be spinning clockwise, so the flywheel is going to be spinning clockwise to shoot out the ball effectively. But up here, and then first we're going to, on the same shaft, we're going to have another pulley which has a belt going all the way up here, which then spins these two. But if we do that, that means these rollers will also be spinning clockwise, and we don't want that because that will just pull the ball right back in and counteract everything we're trying to do. Up here, we want these to spin counterclockwise so it imparts some backspin on the ball to give it stability. And the way we can do that is that gears reverse the rotation. So let's say we have a gear here and a gear here. If this one is spinning one direction, this one is spinning the other. So the way, first of all, let's tackle here. Let's grab a line and see the general distance. So it's roughly, let's say, 3.5 inches. So we can change the target center to 3.5, and let's change this back to 1 to 1 because we don't want any reduction on this one. So we can see the belt teeth of 55 gives us about 3 inches, and then the 60 tooth gives us 3.5433. Let's go with that, a 60 tooth, 3.5433. So we grab a dimension and do 3.5433. That looks pretty good. And so now let's just give us an arbitrary dimension. I'll just dimension it like this. Let's say 1.5. And that looks pretty good. That's fixed in place right there. And so that is the belt that goes up to here. So now we need another belt on the same shaft going up to here. But we're going to add another circle here to represent a gear. So let's put a gear here. And let's say, remember, our gears are 20 dp. So to figure out the diameter of a gear, for a sketch, we can just take a number of teeth, let's say a 36 tooth divided by 20, and it'll spit us out the perfect size. So I'd say that looks pretty good, a 36 tooth gear. So let's make another one here. Actually, let me make that just equal. And so to make these mesh perfectly, is we can just grab these two and make them tangent. So now they're only touching on one point. So now we want is to send a belt direct from this axle here on the flywheel all the way over here. So let's make another line and grab this general length, and we can see it's about 11.5 inches. So let's go back to our belt calculator and go input our target center is 11.5, and we're not going to change in these pulleys because we still want this to be 1 to 1. And we can see with the 140 it's about 11.4, and with the 145 it's about 11.9. Let's go with the 140. So you can see center distance is 11.4173. So let's do that. 11.4173. So you see now that's fixed that position of this gear in relation to everything else. So now that's pretty much done for the power transmission. So I'll go over how this works again. So we have a motor here that spins clockwise, and that clockwise rotation is belted up to here, where this flywheel, this is the main flywheel that's shooting out the ball, is spinning clockwise. And then another pulley on that same shaft is going out to here, to this shaft, where a gear is also on the same shaft, which is spinning clockwise. And the gear that it meshes with will spin counterclockwise, which means this roller will spin counterclockwise. And then because these two are belted together, the rotation direction is the same. So this will be spinning counterclockwise, and this will be spinning counterclockwise, which then shoots out the ball like we want it. I think that's pretty much it for our reference geometry. In the next video, we'll go over how to make our plates, make the belts, and get all the mounting holes in, like basically all the work we need to do in the Part Studio. And then the video after that, we'll go over the full assembly. All right, thank you. Bye-bye.